Hello everyone, my name is Tony. I'll be talking about joint work with Anand Natarajan and Zhang on succinct arguments for QMA. So let me begin by just defining what a succinct argument for QMA is, and then most of this talk will be dedicated to explaining how we can achieve this from standard cryptographic assumptions. So in a succinct argument system for QMA, we have two parties. We have a classical efficient verifier, and we have an untrusted quantum prover. And what makes this an argument system rather than a proof system is that we assume that this prover is efficient. So in particular, later on, we will assume that this prover cannot break standard post-quantum cryptographic assumptions. And now this classical verifier here will get some instance X of a QMA problem. If you're not familiar with QMA, just think of the quantum version of NP. So just like for NP, for yes instances, they're witnesses, but these are quantum states now instead of classical strings. The prover is given the same instance X, and it's also given a state psi that can depend on X. And then verifier and prover interact, and we want that this protocol has three properties. The first is completeness. It says that if X is a yes instance, then an efficient honest prover, given polynomially many copies of the QMA witness as the state psi here, is accepted with high probability. And as a side note, the reason we have to allow this extra input of the state psi here is precisely because we assume that the prover is efficient, so we cannot assume that the prover can make their own copies of the witness state. So we assume that in the honest case, in the complete case, the prover is given polynomially many copies of the QMA instance witness and uses those to convince the verifier. Soundness says that if X is a no instance, then all efficient provers, given any state psi, are rejected with high probability. So these two things here are the properties of an argument system for QMA. And then what makes this succinct is that we want to require that the amount of classical communication that is exchanged is only polylogarithmic in the length of X. Constructing succinct arguments for QMA has been an open problem in crypto for a while. And previously, it was only known how to do this from something called I/O. This is short for indistinguishability obfuscation, which is a sort of insanely powerful cryptographic primitive that's known to imply sort of elusive objects like public key quantum money. And in particular, the sort of post-quantum secure version of I/O that is necessary in this existing protocol here by Bartuszek et al. Is not constructible, as far as we know, at least from standard cryptographic assumptions. Nonetheless, I briefly want to explain how this protocol works, both to contrast it with our approach and also because we will reuse parts of their protocol. So they start from a non-succinct argument system for QMA. So this is, it has the completeness and soundness properties, just like here, but the amount of classical communication is polynomial rather than polylogarithmic in the instance size. And this has famously been constructed by Mahadev a couple of years ago. Then they reduce the question size, and this is where the post-quantum I/O comes in. And then in the second step, they reduce the answer size using some generic compiler based on Killian's protocol. So the thing I want to stress here is that the only place where post-quantum I/O comes in is in reducing the question size. The second step here is completely generic, and we will actually reuse it in our protocol. Our goal is to construct succinct arguments from standard assumptions, which in particular means without post-quantum secure I/O. The problem is that if you start from Mahadev's protocol, like Bartuszek et al. Did, this seems like a very difficult problem because Mahadev's protocol is inherently qubit by qubit. There's some number of qubits in the witness state, and Mahadev's protocol kind of checks them one by one, and for each qubit you have to send over a key to the prover to set up some post-quantum crypto system and so on. And this is why, to reduce question size, this work needed this very powerful primitive of post-quantum I/O to overcome this difficulty of this qubit by qubit verification. Now, in our work where we don't want to use I/O, we take a sort of completely different approach. We don't start from Mahadev's protocol. Instead, we start from a multi-prover proof system for QMA that has long questions and long answers, so it's not succinct. And in particular, the one that we use has been constructed by Grillo in 2018. So the difference to a succinct argument system, like we saw on the previous slide here, is that firstly, we have two provers now rather than one. And the assumption is that these provers may be entangled, but they cannot communicate during the protocol. But the classical verifier can communicate with both of them in the protocol. Secondly, in a proof system, the provers are all powerful, which I've indicated with these little crowns here. So there's no computational assumption at all in this multi-prover proof system. Now what we do is we reduce the question size in this multi-prover proof system. And this we do using information theoretic techniques, in particular something called self-testing or rigidity, which roughly says that if you play one of these multi-prover protocols, also called non-local games, then you can sort of make very precise statements about what has to go on internally inside of one of these provers if they win the game with close to optimal probability. These techniques are very powerful, and they've been developed over a long time, mostly in the context of analyzing the complexity class MIP star, which has been proven to be equal to RE a couple of years ago. Then in a third step, we now switch from the multi-prover to the single prover world. And this is where the computational assumptions will come in. So we use a compiler by Kalai et al. That takes any multi-prover protocol and compiles it cryptographically, so using computational assumptions into a single prover argument system. And then finally, we reduce the answer size using the same generic compiler based on Killian's protocol that the Bartusek et al. Paper from before used. Okay. So really, the key difference in our approach to the existing ones is that we do the question size reduction step in this multi-prover setting where we have access to all of these powerful self-testing tools. And only after we've reduced the question size do we even switch to the single prover setting. And then the rest works as before. So for the rest of this talk, I want to explain step 2 and step 3 in a little bit more detail. Step 1 was known already, and step 4 is the same as in the previous paper. So these are really the two technically difficult steps. Okay, how do we get a question succinct multi-prover proof system for QMA? Well, for this, let me just tell you how this non-succinct multi-prover protocol works. And it works by two tests. The first test I'll call a Hamiltonian test. And for this, one fact that you need to know is that a QMA complete problem is the following. I give you a classical description of a local Hamiltonian, so just some permission matrix that has a particular structure to it. And I ask you to determine the lowest eigenvalue. This is called the ground state energy of this Hamiltonian. This is QMA complete, and this is the problem that we will want to verify. So in this Hamiltonian test, the verifier asks Alice to teleport the ground state of a QMA complete Pauli XXZZ Hamiltonian, so it has only Pauli X and Pauli Z terms, to Bob. And then Bob is supposed to measure Pauli observables provided by the verifier on this teleported state. And this Hamiltonian test has an energy guarantee, which says that if Bob is honest, then the only way for the provers to succeed is if the Hamiltonian indeed has a low energy ground state and Alice teleports that state. Okay, this is fairly easy to prove, because if Bob indeed does honestly measure the Pauli observables as instructed, then the verifier would from that be able to reconstruct the energy of whatever state Bob measured the Pauli observables on. So the only way to convince the verifier that this is a low energy state is if indeed there exists a low energy state, and this is the state that Bob used. Okay, the challenge here is that we don't want to assume that Bob is honest. And for this, we'll use a second test that basically forces Bob to be honest. So this is called the Pauli braiding test, and here the verifier asks the provers to measure Pauli observables on a shared EPR state. And this has a rigidity guarantee or a self-testing guarantee that says that only provers that honestly measure Pauli observables can succeed in the test. Okay, and then we can combine these two. And to combine them, you just need to observe that in both of these cases, all that Bob sees as questions from the verifier is some list of Pauli observables that he's supposed to measure. So he can't tell these two tests apart. He doesn't know which one is being played. So the rigidity guarantee also holds in the Hamiltonian test. And as a consequence, this energy guarantee kicks in because the Pauli braiding test forces Bob to be honest. Okay, so to make this succinct, we'll basically just have to make the Hamiltonian test succinct and the Pauli braiding test succinct. Let me start with the Hamiltonian test. Usually in QMA verification, if we want to use the local Hamiltonian problem as a complete problem, we do this for a local Hamiltonian problem that has inverse polynomial promise gap. And then to get to constant completeness soundness gap for QMA, we just repeat the protocol polynomially many times. This is perfectly fine for normal QMA verification. But if we care about succinctness, then we cannot repeat the protocol polynomial many times because this would also blow up the amount of communication by a polynomial factor. So the solution to this is to first amplify the Hamiltonian to a constant promise gap by taking tensor products. If we do this, the problem that we incur is that the number of terms in the Hamiltonian, if we take polynomially many tensor products, is going to be exponential now. So as a second step, we have to reduce the number of terms in the Hamiltonian to a polynomial. In our paper, we do this cryptographically using a PRG because we ultimately anyway care about argument systems. But I will point out that we also do know how to do this information theoretically. This is work by myself with Thomas Wittig and Tina Zhang. Okay. Now let's do some accounting. We need a constant question size to tell Alice to teleport. This is just an instruction. And we need logarithmically many bits to tell Bob which Hamiltonian terms he is supposed to measure because there's only polynomially many terms. So we need, log of that polynomial number of bits to specify a term. Okay, so this is how we make the Hamiltonian test question succinct. For the Pauli braiding test, this is a little bit more challenging, and we'll encounter a number of problems. And I just want to give you a sort of flavor of the problems that we encounter and roughly sketch the solution. This is going to be a somewhat technical slide, so feel free to skip it if you're not so familiar with the self-testing literature. But we hope that some of these tools are also useful outside of this particular context because they are a more general way to do self-testing of mixed Pauli observables. So I'll mention them briefly. Okay, the first problem that we encounter is that if we amplify the Hamiltonian, like I described on the previous slide, then we introduce mixed X and Z Pauli observables. So Pauli terms of the form, Pauli X, tensor Pauli Z, tensor Pauli X, tensor Pauli Z, whatever. The Pauli braiding test, in contrast, is only designed for all X or all Z observables. So to deal with this, we have to introduce an additional consistency test that extends the Pauli braiding guarantee to mixed X and Z observables. Secondly, if we want to combine the Pauli braiding test and the Hamiltonian test, then the rigidity guarantee from the Pauli braiding test must hold for the distribution of Pauli sampled from the Hamiltonian. So what I mean by this is that the Hamiltonian that we ultimately want to verify the energy of is a sum of Paulis. And we will uniformly sample in the Hamiltonian test, we will uniformly sample one of these Pauli terms. And we need that Bob behaves honestly when asked one of these Pauli questions. So on average, over the distribution of Paulis that we get by sampling uniformly terms from the Hamiltonian, we need that Bob behaves honestly. This, again, is not something that is baked into the existing self-testing analyses, which always deal with uniformly random Paulis. So to do this, we prove a new, what we call a non-uniform Gauss-Hatami theorem that works for any distribution. What this says is it's what is known as a stability theorem for approximate group representations in math. What it says is that if some observables approximately satisfy the relations of the Pauli group, they can be rounded to actual Pauli observables. Finally, we need to de-randomize this Pauli grading test to actually make it question succinct. For this, we use a de-randomization due to de la Salle from 2 years ago, which is a simplification of the original MIP star equals RE approach. This, unfortunately, was only known in Frobenius norm. We need it in some sort of state-dependent norm. This gets very technical, but the solution is to just, do a more direct analysis of de la Salle's de-randomization that firstly requires, it's a bit more natively quantum, so it's maybe more accessible to some audience at least, and it also works in the state-dependent norm. Okay, so these are the ingredients to make the question size polylogarithmic. We first amplify the Hamiltonian, then we reduce the number of terms by just subsampling using a PRG, and then we, in the Pauli grading test, overcome all of these problems by introducing the consistency test and analyzing this de-randomization procedure in a more general way. Okay, so now we've achieved step 2. So I want to spend a couple of minutes explaining how to do step 3. Step 3 uses this compiler by Kalai, Lombardi, Vaikuntanathan, and Zhang. And the way that this works is it takes a multi-prover proof system where, for the sake of concreteness, say the verifier first asks question X and receives answer A from the left prover, and asks question Y and receives answer B from the right prover. Then the compiled version of this game is going to be a protocol where the verifier sends a fully homomorphically encrypted version of the question under some quantum secure homomorphic encryption scheme, which is known to be constructible from standard assumptions. Then the verifier will receive the homomorphically encrypted answer from the prover, and then the rest of the protocol is just played in the clear. Okay, so this is where the computational assumption comes in this fully homomorphic encryption scheme. The idea of this compilation scheme is that what the sort of key property of the multi-prover setting is that the right prover here does not know the question of the left prover. And this compiled game is meant to mimic this property because at the moment when the prover receives question Y, the prover sort of doesn't know what question X is because it was encrypted. The prover can't tell. But because the encryption was homomorphic, the prover can nonetheless answer the first question correctly. Kalai et al. Originally analyzed the classical winning probability of this compiled game. So, what's the winning probability if we only have classical provers? And they proved that the classical winning probability in the compiled game is at most the classical winning probability in the original game. For our purposes, we care about quantum provers, right? We want to compile this, question succinct multi-prover verification protocol for QMA. And this has a quantum prover, so we care about the compiled value for quantum provers. This is much harder to analyze. So previously, the only thing that's really known is due to Natarajan and Zhang from a year ago, who proved that for the CHSH game, which is a very simple multi-prover protocol, the quantum winning probability in the compiled game is indeed bounded by the quantum winning probability in the original game. And also these self-testing results are preserved. So they carry over from the information theoretic or this MIP star world into the cryptographically compiled world. Very recently, there's been another work that has proven that in the limit where the security parameter goes to infinity, this bound holds for the quantum winning probability. The problem is that this does not give us any control over the speed of convergence. So therefore, it's kind of not useful for cryptographic applications because we never know how to pick the security parameter large enough so that this bound holds with some sort of manageable known error. Okay, so what we do is we analyze the compiled version of our question succinct QMA verification protocol, and we prove that for this also the quantum winning probability in the compiled world is bounded by the quantum winning probability in the original game. And this means that if we start from a question succinct sound QMA verification protocol in the multi-prover world, then we've proven that the The compiled version is also a sound single prover question succinct now argument system because it relies on the computational assumption in FHE for QMA. Really, the key technical contribution here is that we have to replace a lot of the self-testing tools from the MIP star literature by what you might call more compilation-friendly equivalents, so equivalents that we can still analyze in this compiled world. Okay, so this explains step 3, how we prove that if we take a question succinct sound QMA verification protocol and compile it, how we can prove that the compiled version is still sound. Okay, so the main thing I've talked about is a succinct argument system for QMA, and we achieve this from standard assumptions by essentially combining the best of MIP star techniques, namely question reduction, with the best of cryptographic techniques, namely this answer reduction protocol using Killian's protocol. And you combine these two things using this cryptographic compilation procedure. The sort of moral lesson from this is that this technique of compiling non-local games really allows us to utilize powerful techniques from the self-testing literature in cryptographic protocols. So I said at the start that the difficulty in the prior approaches was that Mahadev's protocol is very qubit by qubit, and if you want to analyze this sort of cryptographically, it's unclear how to compress the keys for the questions and so on. We sort of completely circumvent this whole issue because the MIP star inspired question reduction procedure is very global. It doesn't have any cryptographic anything. It's a purely information theoretic thing. And then this compilation procedure allows us to import these results into the cryptographic setting. The big open question here is still whether this compilation procedure is sound. So it's sound for quantum provers as well for general games. I mentioned this asymptotic result, but we would like some explicit non-asymptotic bound on the compiled value of any game as a function of the value, so the optimal winning probability of the original non-compiled game. And finally, there's also some hope that these compiled games might lead to better verification protocols. All right, thank you very much for listening.